Hello, friends and neighbors. I'm going to show you now how to use the apportionment spreadsheet to do the computations you need to make your apportionment easier to do. So starting with the Cascadia application project, let's suppose I decide to keep the 4 states we have: Idaho, Washington, Oregon, and BC, British Columbia. And so I take about 30 seconds to go on the internet and look up their populations. What I've done here is made up some numbers that are similar to but not actual real numbers. Okay. So to use this spreadsheet, the red part is where I do the data entry. That's where I make my own changes. And the yellow part, well, that's just input for me to read. So I'm going to give the names of the states: Idaho, Washington, Oregon is fine, and British Columbia. Okie doke. So then I decide how many states, how many seats I've got in the house. The house size is 16 because the assignment says to make it 4 times the number of states. Okay. Now all the rest of this is done automatically for me. It has automatically computed the population. That's that. By summing those. It has automatically computed the standard divisor by dividing those. Okay. Now, using the Hamilton method, I go to the section that says Hamilton. I scroll down. All of this is just information. Step 1 and Step 2 really just do the apportionment for me. And I look here at the important part where it says I have apportioned 13 seats using Hamilton, and that's, of course, not correct. I need 16. So I'm going to come down to Step 3 here, where I'm going to default to having, I'm going to start with the initial allocation, 1633, 1633. And then, with Hamilton, to go to the upper quota, I look for those states that have the largest fraction remaining. Well, BC has 0.94 remaining, so they're going to get an extra seat. They get their upper quota. Oregon has 0.9. They get their upper quota. And then I've got to apportion one more because I'm up to 15. And so the last one, Washington has 0.7 as its fraction, so they get their upper quota. So upper quota goes to Washington, the largest state, Oregon, and British Columbia. Idaho does not get their upper quota. They are staying with their lower quota because their fraction is lower. And that apportions the 16 I need. That's how you do it with Hamilton. Hamilton is a quota method, so everybody gets either their lower quota or their upper quota. Lower quota for 1.456 would be 1, and the upper quota is 2. Lower quota is just the next integer down from the initial quota, and the upper quota is the next integer up, the next whole number up. Okay. Now let's consider the Lowndes method. The Lowndes method is very similar to the Hamilton method. It is also a quota method. However, it has a tendency to favor the smaller states, whereas Hamilton has a tendency to favor the larger states. So the first several steps are all identical. And again, we have apportioned 13, which means I need to give 3 more seats to 3 more states. I'm going to start with the initial allocation as given here at 1633. And now I'm going to change it by taking the looking at the step 4 ratio and taking the largest one to give them an extra seat, to give them their upper quota. And we can see that 0.46 is the largest, so Idaho is going to get their upper quota. The next largest is British Columbia. They will get their upper quota. And Oregon has the next largest. They will get their upper quota. And notice that Washington gets their lower quota. So in this partition, the largest state gets their lower quota, and the smallest state gets their upper quota. Just the opposite of what we got when we did this with Hamilton. Hamilton favors larger states. Lowndes favors smaller states. and I stop when I got 16 partitioned. Those are the two quota methods. The other three methods, Jefferson, Webster, and Hill-Huntington, are all examples of divisor methods, and we do those by changing the divisor instead of just using the standard divisor. Okay, let's look at Jefferson. All of the computations are done for us, and it gives us the apportionment based on lower quotas. And it turns out that we have only apportioned 13 in this way. And this note here in cell E152 says too small, use a smaller divisor. So I'll scroll down to the next step where I can do that. And the standard divisor, I'm going to scroll up a bit. Now I'm going to scroll over. Okay. The standard divisor shows us with, it's right here. Here's the standard divisor. I'm going to paste that into my cell. Okay. And this red cell, as always, red is the cell that we do editing in. So it says here in my note that it is too small and I need to use a smaller divisor. So I will start with, I like nice integer values, whole numbers. So I'm going to place all of these numbers with zeros and see if that works. And it does work. In that one step, just trying that number sort of arbitrarily worked. It says here, just right, we are done. I've now apportioned 1 to Idaho, 7 to Washington, 4 to Oregon, and 4 to BC. Okay, and you'll notice that this method, the Jefferson method, is very similar to Hamilton in that they both favor large states. But it's also different from Hamilton in that I have to choose a divisor, and I do so by trial and error. Okay. So that's the Jefferson method, and it gives me 1744 with these made-up numbers. These are not real state numbers. Webster is similar to Jefferson, except instead of starting with rounding down the lower quota, it uses standard rounding rules. That's the only difference. But because of that difference, it has a tendency to be relatively size neutral. It does not favor large or small states. So what do we know? Hamilton and Jefferson both favor large states. Lowndes favors small states. Hamilton and Lowndes are both quota methods. Webster, Hill-Huntington, and Jefferson are all divisor methods. Okay, let's play with Webster now. Scrolling down, and basically I'm skipping everything except when I get to this point where it says, just right, we are done. That means the initial quota was sufficient, and I don't need to take any more steps. I'm going to scroll down just to show you where we would take additional steps if they were required. Here's the standard divisor. I'm going to put that in here. And it works, but if I needed to make a divisor that was smaller or larger, I would do that. So I'm going to show you what a smaller one would look like. I like to start with my trial divisors by just replacing everything with a 0. And when I do that, it apportions too much, too big, and so I need to use a bigger divisor. That doesn't surprise me. Another thing that I might do would be to try 11 with all those zeros, and that would be too small. I would need to use a smaller divisor. The standard divisor works, so none of this is actually necessary with this example. But if it were necessary, I would go 5. For example, that would be another divisor that works. There's essentially an infinite number of divisors that work. Okay. Last method is Hill-Huntington. Very similar to Webster. The difference is how the rounding is done. Instead of using standard rounding rules, it computes the geometric mean between the upper and lower quota and uses that as a tipping point. If the values, if a certain initial quota is larger than the geometric mean of the upper and lower quota, then we round up to the nearest integer. And if it's smaller, then we round down. Okay, so in this case, using the Hill-Huntington method, we saw that it was too big, and we have to use a bigger divisor. We allocated too many seats. We allocated 17, and we've only got 16 to allocate. So let's scroll over a little bit. And I guess I need a little more room, so I'm going to not see what the states are. The standard divisor, let's start with that. Standard divisor here. But I need something that is, like it says, bigger than the standard divisor. So what I'm going to do is change, just for fun, so I'm working with nice, convenient whole numbers. Change all this to 0 except the 4. I'm going to change that to a 5. Okay, that's not big enough. My note down here in cell M303 says that it's not, it's too big and I need a bigger divisor. So instead of 05, I'm going to start with 10. That's too small, so I need a smaller divisor. Now I know it's between 110 and 105. So let's try 109. Too small, need a smaller divisor. Try 108. That's it. 108 works. So an allocation of 1744. Idaho gets 1, Washington gets 7, Oregon and BC each get 4. You'll notice 1744 is the same allocation we got for the Webster method. So Webster and Hill-Huntington agree in this case. That's not always going to happen, but it's happening now. 1744 with Hill-Huntington, 1744 with Webster, 1744 with Hamilton, with Jefferson rather, and with Hamilton it is 2644. I'm sorry, that's not Hamilton. That's Lowndes is 2644, the one that favors small states, and then 1744 is what we get with Hamilton. So actually, all but Lowndes in this case give 1744. All right, that's how you use this spreadsheet to do apportionment. If you've got a context that has 6 states like A, B, C, D, E, F. Something, just call them A, B, C, D, E, F, and maybe it's got different numbers like, I don't know, 100, 200, 107,